Hi everyone, today we're going to be going over Snowball Earth, or more specifically, Slushball Earth. And we're going to get into why these changes need to be made to that title a little bit later. But yeah, throughout Earth's history, there have been multiple Snowball Earth events, and there is more recent evidence for them being more like slush balls than actual snowballs, meaning not totally covered in ice. But the gist of this video is the major glaciations throughout Earth's history that have nearly covered Earth in ice. First, we'll talk about what Snowball Earth is, when it occurred, or when they occurred, why did it occur, what started it, how do we know, what's our evidence, what ended these events, and how did it change evolution biologically as well as the environment. So to answer the first question, what is Snowball Earth, I kind of already mentioned that this just refers to periods in Earth's history in which Earth was completely covered in ice. And like I already said, probably not completely covered in ice, but we'll talk about that later. And I want to make sure that y'all understand how cool this is, because if you think about it, these periods in Earth's history where Earth was like a snowball are kind of analogous to other ice-covered planets and moons, such as Europa, which is an ice-covered moon that people are curious whether there's life under that ice. And so if Earth had it, why couldn't Europa or other ice-covered moons? And so sometimes I like to think about, what if Earth went into another snowball event millions of years down the road, and then Europa, for example, was completely warm and flourishing? I mean, maybe during Earth's snowball Earth, that could have been the case. We don't know. And so it's really cool for me to think, well, maybe the tables have turned and maybe they'll turn again. And we just don't know. Maybe it's just this time in Earth's history is Earth's time. But I just think it's really cool to think about. And that's why, one of the reasons why studying these snowball Earth events is so cool. And let me preface this by studying snowball Earth is not only cool for reasons like life on other worlds, but also because reconstructing Earth history, like I've said in my previous videos, is important for projecting future climate conditions and climate changes and understanding how the major biogeochemical cycles work on Earth, which is very important for our climate projections, etc. And I've talked about this in the previous couple videos over biogeochemical cycles. But anyway, this is very important and also, I think, really cool. So let's move on from my huge teen girl crush on Snowball Earth and let's get into the nitty-gritty details of what we're going to go over in this video. So the second question is, when did Snowball Earth occur? Well, there were two major events that people kind of sometimes clump into one Snowball Earth event, which is how Snowball Earth got its name as a single event. These two major events are the Sturtian glaciation, which occurred around 716 million years ago, and the Marinoan glaciation, which occurred around 650 to 635 million years ago. However, there was also another possible Snowball Earth event that I am partial to, because you guys know I love the Great Oxidation event, which happened way before these two major Snowball Earth events. And that oxidation event was also associated with a glaciation event. And this is sometimes considered the first Snowball Earth event, but because it's so much older, 2.1 billion years ago, over a billion years before the other two Snowball Earth events, it's hard to find a lot of geologic evidence, a lot of geochemical evidence, and so it's not as well documented, but we'll also be talking about that today. And that Snowball Earth event is called the Macanine glaciation. I'm so sorry, you guys. I say things so bad. I swear my information is good. It's just I don't know how to say words, but the content is there, so let's move on. And we can see this glaciation occurred on the graph here between 2 and 2.5 billion years ago, right where we see the Great Oxidation event occur. And then we have the Sturtian over here, the second peak. So global glaciations, it's the second peak. And then we have the Marinoan glaciation is that third peak. So since most of our evidence is for the Sturtian and Marinoan glaciations or Snowball Earths, we're going to talk mostly about those today, but I will throw some bits and pieces that we do have of the first Snowball Earth event, because we do have some information on that, but we'll mainly be focusing on the second two Snowball Earth events. So now we move on to what kicked off these Snowball Earth events. A big component is Rodinia breakup. Rodinia was a supercontinent that formed around 1 billion years ago, and it began to break break up around 750 million years ago, a few million years before the beginning of the Sturtian glaciation. This supercontinent breakup is really important for starting that cooling trend because this abrupt increase in weathering due to the abrupt increase in tectonic activity led to a huge carbon sink. If you're unsure how this works, I talk way more about weathering as a carbon sink in my Biogeochemical Cycles Part 2 video, so you can go check that out, or I'll put it up here in the corner so you can click on that and go watch that first. But basically, silicate weathering causes the transport of carbon to ocean basins where calcium carbonate forms, and those carbonate minerals get buried and cause that carbon to be stored for a long time until subduction melts that carbonate material and causes the carbon to come up out of the volcano as carbon dioxide. So in this cycle, the volcanic activity is the carbon source and the weathering is the carbon sink. However, volcanic activity can not only cause warming, but can also cause cooling. And this was also a big proponent in kicking off these snowball Earth events. And if you want to know more about things that control climate and change the climate, either warming or cooling and feedbacks and all that, you can also watch my climate video. I talk about how volcanoes can warm and cool in that video as well. So now getting to this volcanic activity that contributed to the initiation of the Sturtian glaciation, that first or second, depending on how you look at it, major snowball Earth event that started around 716 million years ago. That glaciation was kicked off by major volcanic eruptions that started around 18 million years before that glaciation began. Now, as we just mentioned, volcanoes can act as a carbon source because what they're releasing into the atmosphere technically contains a lot of carbon dioxide and therefore greenhouse gas and therefore can cause warming. However, volcanoes can also cause cooling due to sulfur emission. What comes out of a volcano also has a lot of sulfur in it. Sulfur dioxide, hydrogen sulfide, and so these sulfur compounds get into the atmosphere and they convert to sulfate. And sulfate acts as a really good cloud condensation nuclei. Basically, this just means that clouds form due to this increase in sulfate content in the atmosphere, and these clouds increase Earth's albedo drastically. However, the sulfur emissions from the volcano, in order to cause a long-term effect on Earth's climate, must go up into the stratosphere, which is the second layer of the atmosphere going up from Earth's ground. The first layer is the troposphere. If the sulfur emissions only reach up into the troposphere, the sulfate cooling effect will only last 1 to 3 weeks. Whereas if they go up into the stratosphere, that sulfate cooling effect will be lengthened to a timescale of years rather than weeks. And so if enough volcanic eruptions are occurring all at once and over a long period of time throughout Earth's history that release emissions of sulfur up into the stratosphere, this will cause a pretty long-term and drastic cooling effect on Earth's climate that could contribute to kicking off a snowball Earth event. So in the case of the Sturtian glaciation, there were extensive volcanic eruptions in which there's evidence for their ash going all the way up to the stratosphere, causing a long-term sulfate cooling trend, and these extensive volcanic eruptions increased Earth's albedo long enough to help kick off this icehouse climate that caused the snowball Earths. And we can see the evidence for these eruptions today in the Franklin Large Igneous Province. Like we can see on the map, this igneous province is 730 to 710 million years old, and so because we know the dates line up, this is very likely to have contributed to this first of the two major glaciations that we call snowball Earth. However, I want to stress that this alone couldn't necessarily cause a snowball Earth event. It could cause a little bit of cooling, but all of these causes we're talking about are not standalone causes, and it's not an either-or situation. All of these causes caused the perfect storm that caused these snowball Earth events. And two additional factors to weathering and volcanic activity include the sun's intensity, which was 7% less intense than today. Yes, our sun in the middle of our solar system is continuously gaining intensity due to the nuclear reactions that are occurring in it, and at this period in time, 700 million years ago, it was about 7% less intense than today. And lastly, the positive feedback effect of ice is the most effective cause of snowball Earth events. Now, this cause has to be kicked off by other causes first before it can really take hold, but once ice cover starts to increase over Earth's surface, the albedo positive feedback, meaning the positive feedback associated with the reflection of the ice, will become so strong that it will take over over and cause further and further cooling. And if it's left unchecked, it'll cover the entire Earth in ice. So our next question is, what is our evidence for these snowball Earth events? And we talked a little bit about how we know Rodinia was breaking up at that time and the large igneous province is some evidence, but there are many other lines of evidence that are really important for proving these snowball Earth events happened. And these include global glacial deposits, banded iron formations, cap carbonates, carbon isotopes, boron isotopes, iridium, and substance. So let's get started with glacial deposits. In this slide, we can see a global distribution of the glacial deposits and BIFs, which we'll get to in a second, of the Sturtian and Marinoan glaciations respectively. All the yellow dots are the glacial deposits. The red dots are banded iron formations, which we'll get to in the next slide. But first, we need to discuss what these glacial deposits are associated with and how that's important. So first, the association of glacial and glacial-marine deposits with carbonate successions, which typically occur in the warmest parts of the ocean, is important because this is emphasizing that glaciers were at the warmest parts on Earth and the warmest parts in the ocean. And if they're there, they're everywhere. Additionally, deposition of glacial and glacial-marine strata close to the paleo-equator, where the equator would have been back then, during not only the Marinoan and the Sturtian glaciations, but also the Mancunian glaciation, that old one we talked about 2.1 billion years ago. That distribution of glaciers near the equator is really important evidence for having glaciers literally everywhere on Earth at the time. And this comes from really robust paleomagnetic data. Now, I am no expert in paleomagnetic data, so I'm not going to get into that. But if you want to look into it on your own, there's a link in my description for a website that basically is all about snowball Earth, and they talk about paleomagnetic data and paleomagnetic evidence for snowball Earth events quite a bit in that website, so you can check that out. However, the main two things I want to point out for this glacial deposit evidence is that both the association with carbonates and the distribution near the paleo-equator emphasize the global extent of these glaciations. If you do want to know more about what glacial-marine means and how glacial-marine deposition takes place, you can watch my video over glacial-marine deposition for more on that. Moving on to banded iron formations, or what we saw in the previous slide were the red dots called BIFs. BIF deposits were really important for the Great Oxidation Event, which I talk a lot about in the Great Oxidation Event video, which you can check out. I'll put it right here for you. However, these BIFs were also important during these snowball Earth events. BIFs, which were formed after 1.9 billion years ago, are exclusively associated with glacial-marine strata, which we can see in the bottom pictures here. These are banded iron formations with huge drop stones in them, indicating their association with glacial deposits. Additionally, their deposition in the first place is indicative of widespread anoxia consistent with an ice-covered ocean. So oxygen-depleted oceans would occur in an ice-covered regime, because we typically assume that the ice cover is hindering photosynthetic processes in the surface ocean, causing oxygen to become depleted over time during these snowball Earth events. Additionally, a shift in hydrothermal regime is thought to have contributed to these banded iron formations as well, because an increase in hydrothermal activity relative to continental weathering, which would have decreased or totally stopped during these periods, would have caused an increased concentration of iron in the ocean, contributing to the deposition of these banded iron formations. The next piece of evidence we have is cap carbonates. Deposition of post-glacial cap carbonates on continental margins and inland seas after the Sturtian and Marinoan glaciations have been interpreted to be due to the greenhouse aftermath of the snowball Earths. We can see in this picture step by step what might have happened during these two major snowball Earth events, and this includes the first picture where we have complete ice cover, and then we have the second, which is the beginning of the meltdown period, where warming and meltwater production causes hyperstratified ocean conditions during the end of these snowball Earth events, and then huge sea level rise due to not only ice melting but also increased mid-ocean ridge spreading. And this sea level rise caused huge carbonate shelf production and deposition of carbonates, as well as transgression of eperic seas in which more carbonates were deposited deposited on top of all the glacial strata. Here's a picture similar to the one we saw in the previous slide of BIFs, where we have these lower glacial sediments with drop stones and everything indicating glacial meltdown stage and deposition during the end of these snowball events. And then we have the carbonate sediments capping all of these glacial sediments. Getting into the geochemical evidence, we have a couple different isotope systems we'll talk about, but the main one is carbon isotopes. Carbon isotope ratios in these capped carbonates that were deposited following these glaciation events decrease dramatically. This drop in carbon isotope ratios is seen in this graph right after the Sturtian glaciation and right after the Marinoan glaciation, and these drops are due to an abrupt increase in respiration and methane hydrate melting. I talk a lot more about carbon isotope fractionation in my carbon isotopes video, as well as the biogeochemical cycles part 1 video if you want to check that out. But basically, photosynthetic processes as well as biological methanogenic processes cause the uptake of lighter carbon isotopes, and so when these are all released due to respiration or oxidation of organic carbon, as well as methane hydrate melting and being released back into the atmosphere, all of this light carbon is being released into the atmosphere, causing these huge drops in the carbon isotope composition during this abrupt warming period following these glaciations. The other isotope system we'll talk about for snowball Earth evidence is boron isotopes. Boron isotope ratios in the carbonates deposited before and after the Marinoan glaciation are shown in this graph. As we can see, there was a sharp decrease in boron isotope ratio directly following the glaciation event, and this can be interpreted in a couple ways. Typically, continental weathering lowers the boron isotope ratios of carbonates, and hydrothermal exchange raises it. Therefore, the boron isotope composition of seawater is expected to rise during the snowball Earth event. However, the boron isotope composition did not rise. In fact, it decreased, and this has been thought to be due to a large decrease in seawater pH, which would be consistent with a large increase in CO2, which would also be consistent with glaciation. So this can be interpreted in a couple ways, and typically people have interpreted this huge drop as it being due to the decrease in pH. The last bit of geochemical evidence that we're going to talk about for these snowball Earth events is iridium. Iridium is an element that we probably have all heard has to do with the dino extinction event, basically the KT boundary or the KT extinction event in the rock record. We see a global layer of iridium with high enough concentrations that we know there was an asteroid impact, and we actually know where the impact occurred, and we found the crater. We have all this evidence for extraterrestrial impact that caused that layer of iridium found at the KT boundary. However, there is an iridium layer also found in association with these glaciation events. As we can see in these spikes on these two graphs, this iridium is found at the base of the Sturtian and Marinoan cap carbonates. Right after the glaciation events, there's this global iridium occurring, and this is not necessarily due to an asteroid impact. Actually, this extraterrestrial dust, per se, or space dust, if you will, is allowed to accumulate for millions of years during these periods of glaciation because the Earth is covered with ice. And so this actually normal phenomenon of space dust accumulating would typically go pretty much unnoticed in the rock record because the concentration would remain pretty low and continuously be depositing in the rock record. However, when you have this period of glaciation, the iridium accumulates on top and within the ice, and then upon deglaciation is finally allowed to become released and deposited in the rock record. And the amount of iridium that built up in the ice before it was finally able to release upon deglaciation actually gives a good estimate for how long the glaciation events lasted. Based on the rate at which extraterrestrial dust accumulates on Earth during the last 65 million years or over the course of the Cenozoic era, this would suggest the glaciations lasted at least 12 million years. The last piece of evidence we'll be going over for these snowball Earth events is subsidence. Deep flooding of previous shallow water shelves and platforms after the Sturtian and Marinoan meltdowns, meaning after everything melted away and the warming began, suggest tectonic subsidence due to having been covered in ice for millions of years. This is typical because you would expect subsidence after millions of years covered in glaciers. I mean, we already know that glaciers are strong enough forces to carve valleys, to cause depressions in continental crust that later become filled with lakes, etc. So I feel like this subsidence piece of evidence that we see after these glaciation periods is pretty much to be expected. So now that we've gone over what snowball Earth is, or what people are referring to when they say snowball Earth, and when these snowball Earth events occurred and why they occurred, what kicked these events off, and what our evidence is, or at least the evidence I've shared in this video, I want to stress that there are a lot of other lines of geochemical and geophysical and biological evidence that I just haven't gotten into because of the time of this video, but I think I hit the main ones. So now we can move on to what ended these events and how it changed the environment as well as biology. So what ended these events? We talked about in the beginning how weathering is a carbon sink and volcanic emissions acts as a carbon source. So because weathering is slow during glaciations while volcanic CO2 emissions is not affected really, this can cause CO2 to build up over millions of years during these glaciation events, causing an extreme greenhouse effect directly following the snowball Earth events. Another major factor that contributed to the extreme warming effect that followed the glaciation events is the positive albedo effect that we talked about earlier. This positive feedback does not only operate in the direction of increasing cooling, it can also work in reverse. When the ice melts, it decreases Earth's albedo and continuously compounds that warming effect. So that also contributed to extreme greenhouse climate following the snowball Earth events. The last major factor that contributed to the end of these snowball Earths is increased hydrothermal activity. This was likely due to increased seafloor spreading rate at mid-ocean ridges, which also was a contributing factor to abrupt sea level rise in addition to the melting of the glaciers, which also caused sea level rise. And this, like we mentioned earlier, contributed to the deposition of carbonates which overlie these glacial deposits. So now the question we're all wondering, what about biology? And what was it at the beginning that you changed the title to, Rachel? Oh yeah, slush ball Earth. Why did you mention that? You haven't talked about it at all. Well, here's where it comes into play. There's some geological and geochemical evidence that kind of suggests that maybe Earth wasn't completely covered in ice, and maybe the hydrologic system was still running a little bit, suggesting more of a slush ball Earth than a snowball Earth. But the major line of evidence that suggests that it was more of a slush ball than a snowball is biology. The fact that biology got through these events really supports the idea of slush ball rather than snowball. Either that, or there was thin ice that allowed sunlight through and photosynthesis to continue, or life could have lived on top of the ice, and this is not unheard of. There is bacteria that can live in snow and ice today, so that is possible, but it's still largely unknown which one of these or all three of these conditions were present on Earth at this time: slush ball, thin ice, or life on top of the ice. But the other thing to ask ourselves about biology and snowball Earth is, didn't biology totally benefit from this situation? It not only survived, but the timing of these snowball Earth events lined up with some major evolutionary advances directly following these events. So were they beneficial, and how did that work? Well, the timing does suggest that eukaryotes evolved directly after or even during the Mackenyian glaciation around 2.4 to 2.1 billion years ago, and that multicellular macroscopic animal life evolved directly after the Sturtian and Marinoan snowball Earth events. So I already discussed endosymbiosis and the evolution of eukaryotic life in my life origins video if you want to check that out. And for that reason, in this video, I'm going to be focusing mainly on the evolution of multicellular life and how that's thought to be associated with snowball Earth. So these glaciation events caused the extinction of many of the species that were living during this time, forcing a handful of individual organisms to become dependent on one another, meaning that single cells gave up their reproduction ability to gain more specialized functions, basically lending themselves and their entire purpose to their colony of cells that they have now clumped up with to get through this period, rather than only caring about themselves and surviving on their own, because they needed each other. And this is called kin selection. We can see in the picture to the bottom right that we have a single-celled protist shown in this step 1 of this diagram, and then we have a colony of single-celled organisms start to form, and then this colony starts to depend on each other, and their functions begin to evolve and work for the greater good of their colony rather than just themselves. And so some cells lose their reproduction ability and gain more specific functions that will help the colony, but in doing so they cannot survive any longer on their own. And this kicks off multicellular evolution. This has actually been reproduced in the lab. As we can see on the bottom left, we have these real-life microscopic images of these single-celled organisms that over the course of just a couple weeks in strained conditions become a colony of cells that will eventually lead to multicellular life that can no longer separate its cells and reproduce individually. So to recap these major snow or slush ball events, we have the Macanian on the left side of this slide occurring around 2.4 to 2.1 billion years ago. Then we have over a billion years ago by to get to the Sturtian and Marinoan glaciations around 716 million years ago, and again at around 635 million years ago.